Alright, hell yeah. So I'm excited about today's video because it should be fairly concise and fairly short. We just have 5 pages of this. And hell yeah, well we're going to go, well let's just read it. So free fall is nearly constant near the surface of the Earth. So we have an equation that says acceleration is close to 10. I'm just going to use 10 for this, 9.8, whatever. But now the question is acceleration a function of time? And because it's constant, like, is it a function of time? And yes, it is. And so the definition of a function is you have an independent variable that I can put in, hey, at 0 seconds, when I drop something, what's the acceleration? It's going to be 10. In 2 seconds, what's the acceleration? That's going to be what I insert into my function. And guess what? The output's going to be 10. So even though there's no t anywhere in sight, it's still a function of time. So I wanted to know, well, is it a function of velocity and position? And yes. And so we're going to explore that because I thought I was making a mistake and just being clever at the same time by doing this little trick. So acceleration as a function of time might get written just as 10, just with this single number. And this isn't a mistake because we kind of checked it. So I wrote it as this. Acceleration as a function of time is 10 times t to the 0. Any input value to the 0 is going to be 1. So this is just 10 times 1. So it mathematically works, except that 0 to the 0 is not defined. And so we're going to show how we can use, and this is great going to Google, typing in, and then just seeing kind of what pops out. And so that's going to be in the next page. But anyway, let's try this one. So even though it's not defined at t is equal to 0, let's see if we can use this same, because this is what I was saying. It's like, hey, acceleration is a function of time, and it's a function of velocity, and it's a function of position. You can write them all together. This is 10 t to the naught, v to the naught, x to the naught. You put any value of position, velocity, and time in here. These just go to 1, and hey, your acceleration is constant. So this kind of shows that. I just put a generic x here, but let's say this x represented the time. And so I want to know 10t to the naught, because acceleration is dv dt, and when we separate variables, we can integrate this, and we can get our function for velocity. Velocity is a function of time. And so let's integrate just a basic equation, x to the 0 dx, and see what we get. We're going to use the power rule, where we have x, the power goes 0 plus 1, and then we're going to divide by 0 plus 1. So this is x to the 1 divided by 1. This is x, and then remember your constant. Let's try to take the derivative. And so we have the derivative of x to the 0. I'm going to bring down the power, and then I'm going to drop the power by 1. Because I brought down the power, everything that I do here is going to be insignificant because it's going to be multiplied by 0. Cool. So using this, it works just fine with the calculus. All right, hell yeah. So now let's graph acceleration as 10 meters per second. I'm going to put my x-axis as time, my y-axis is acceleration, and then here's 10. And I mistakenly, let's just have this start at 0 and be bounded. Time can only be 0 to infinity. So that's what I have. And so time can be any value greater than or equal to 0, and the output and the acceleration is 10. So this is my input. I can come anywhere along this axis and then choose this value, and then come up here and I'll have TA. Very similar to xy, and that's the value at this input. Hell yeah. All right, so then the aha moment from Google, I didn't come up with this aha moment, is that this is a line. And so we know the equation for a line. Y is equal to mx plus b. This line has 0 slope, so the slope is 0. B is the y-intercept, so that's 10. So B is the y-intercept of 10, m is the slope of 0, and then on Google, they just changed the y-intercept b to k, and then our variable x is t in this case, and then even though that we have y, even y, like y could equal a, and that's what we'll do on the next page. But now that we have this equation, acceleration, I'm going to write it one more time. Acceleration is 0 times t plus 10. So this is the equation that I should be using, even though actually, as long as Google's fine with it, I like this way. Acceleration is a function of time. This is 10t to the naught, and then when I use integration, I kind of know that that variable is there. And, you know what I mean, this sets it up. Like what? Because if it is an equation where I'm saying, hey, this is the output, and it's an equation, you know what I mean? Does that mean it has to have an input? It seems like it. And this is where I really like this video and this problem, just because I think mathematic at its most basic is actually where it gets hard. I think we all know how to integrate x squared, but if you had to integrate 0, that's the one coming into this video. It's like, what the hell does that even mean? Integrate 0. You know, and then you get a constant. When you integrate 0, you know what I mean, with a variable, you get a constant. What the hell does that mean? If you look at this as the antiderivative, I'm just going to say words, but that means that when you take this and take the derivative of it, you're going to get something that's 0, because this function is a constant and will have a slope of 0. So if we go the other way, if we have this as our function, a constant function, we know it has 0 slope, the derivative should reflect that. So hell yeah. And I thought that was a good one. But yeah, doing things at the most basic can be very difficult. Alright, hell yeah. So I think we can move on. So we graph this. We got our equation a is equal to 0t plus 10. Hell yeah. So now I'm going to graph all three of them. I'm going to use acceleration as a function of time, as a function of velocity, and as a function of position. I'm going to use three, y is equal to mx plus b, because we do have three different lines here. The y is a in all cases, so the y is a. That's our acceleration. The slope is just the slope of the line. That's going to be 0 for all three. The generic, this is our independent variable. And so this is going to be t, this is going to be v, and this is going to be x. And then b is where it intercepts the y-intercept at 10. So here's three different equations. This is acceleration as a function of time, this is acceleration as a function of velocity, and this is acceleration as a function of position. And so, yeah, so now we can integrate these. And yeah, I guess this is typically the one you integrate, because acceleration by definition is dv dt. And so we have change in velocity with respect to change in time, and that's going to be 0t plus 10. It's going to be a constant. I can separate variables, get the dt over there, and I got a dv right here. I think this is the correct way to do it. You know what I mean? Your v final minus v initial is equal to your integration on this side, integrating this with respect to t. But yeah, this final minus initial is this is just vt is equal to 10t plus c, where this is v final, that's v2, and then this v1 is just to the other side. So you could say this is right there, this is v1, and then this is v2. We don't have to really go into that, but hell yeah. Just the whole idea is just like, hey, when I have something that's a constant, and it's a function of time, but I don't see a t, like what can I do? And I can do this. I can say this is a line and it's 0t plus that constant. And the integration works out. If you wanted, we did this integration over here. Hey, it's the integration of these with respect to t. So I can set up, I can FOIL in the dt to right there and there. And I can do the integration of 0t dt plus the integration of 10 dt. This constant comes out. This constant of 0 comes out. And again, we have that same situation. Anything that happens in here is meaningless because this 0 will kind of cancel it out. But we do have t to the 1 plus 1 divided by 1 plus 1. That's the power rule. This is dt just becomes t. And even right here, you could say, hey, could there just be a t to the 0? Sure, this is t to the 0 dt. And this goes t to the 0 plus 1 divided by 0 plus 1. And that's just t. Alright, hell yeah. But I like that kind of stuff where you're just like, ooh, at the very basic, things get confusing because, you know, something that's a function is just one value, it seems like. You just have acceleration as 10. It's really difficult to see that you're actually inputting in independent variables from 0 to however much time you want to do. Hell yeah, we're doing pretty good. So, alright, so here's the 2. If I'm ever going to use acceleration as a function of time, I still probably will use this, 10t to the 0, even though at t is equal to 0, 0 to the 0 is undefined. So just keep that in mind. If I want to separate variables and integrate, I can get my velocity function is just going to be, and I really, oh yeah, finished it right here, which is just 10t plus c. Or I could say, hey, acceleration is a function of time. It's a constant. That's a line. The slope is going to be 0. The independent variable is going to be t. The y-intercept is going to be 10. So I can kind of see that. Even though it's harder, it's easier just to be like, wait a minute. If I just put in any t, you know what I mean, then it's going to be 10. And so that's where t to the 0 is pretty sweet. How about at 2 seconds? 2 to the 0, that's 1. How about at 5 seconds? 5 to the 0, that's 1. And then 10 times 1 is 10, so the value is always that constant. This, if I input any value of time in here, well, obviously the 0 cancels it out, and then we have that y-intercept of 10. When we integrate this, it's, again, don't get confused over here. This is 0 times t. When we integrate it, the constant pops out and just cancels everything. So this integration is 10 dt goes to 10t plus a constant. Hell yeah. So that's it. And so I did Google this. Is a function y is a constant? Yeah, so if I have y, if I have a function that's a constant, could you say that it is a function of x to the 0? So I said if I have, you know, yx, if I just have this, it's 5, so y is equal to 5. Could I say this is y is equal to 5x to the 0? That's what I'm saying here. And it says, yes, you can. You can say it's y is equal to the constant k, and then you could also say it's y is equal to kx to the 0, or they said y is equal to 0x plus k. So those are the three that obviously you're just going to see it like this, but you can use those other two. But it does say the domain excludes x to the 0 for x to there. And hell yeah. But you never know. That could be something where 0 to the 0 just gets defined as 1 just by mathematicians, but they haven't yet. Okay, hell yeah. And then I said, can I write acceleration as a function of time? You know, can I write the acceleration equation like this? And it says, sure, go for it. Just make sure that t to the 0 is undefined. And then I said, is it more accurate to write acceleration as this or this? And they say both expressions are mathematically equivalent. And this is kind of fascinating because as long as the inputs get the outputs, then you have an equation that jives. You know what I mean? That's where you could have complicated equations where you're just adding fluff to it. You know what I mean? Where it could be simplified. But these two things are drastically different formats. And I think that's kind of unique for this. Hell yeah, about 15 minutes. So we're doing pretty good. And that's it. So that was my video for today. And hell yeah. So going forward, I'm going to keep my eye on this. Just the fact that, hey, if I'm going to have acceleration as a function of time, and it's going to be 10, this is a line. So that's going to be y is equal to mx plus b. The y is the acceleration, the slope is 0, the independent variable is t, the y-intercept is 10. So now this is acceleration as a function of time. That's what it is, and the units on it are meters per second squared. Hell yeah. So going forward, that's what I'm going to do. And booyah. Alright, so pen drop on this one. Hell yeah.